Have you ever stopped and wondered how an AI actually thinks? I mean, we're surrounded by these systems making huge decisions that affect our lives every single day, everything from loan applications to medical diagnoses. But here's the thing. How can we really trust those decisions if we don't understand them? Well, that's exactly what we're going to crack open today. Let's dive into the fascinating world of explainable AI. And it's not just us asking these questions. The experts are basically shouting it from the rooftops. This quote here says it all. When the stakes are high, a simple yes or no from an algorithm just doesn't cut it anymore. We absolutely need to know the why. This isn't just a nice-to-have feature. It's becoming a critical piece of the puzzle for trust and for accountability. And right there, that's the core of the problem we're here to unpack. What happens when our most powerful tools are also our most mysterious? This single question gets to the very heart of one of the biggest challenges in all of modern technology. So let's talk about this mystery. In the field, it's famously called the black box problem. And frankly, it's a fundamental issue in AI development. So let's take a closer look at what this black box really means for all of us. So what is a black box? Well, imagine a system where you can see the inputs, the data you feed into it, and you can see the outputs, the final decision it spits out. But the process in between, the actual logic, it's completely hidden. It's a mystery. And the wildest part is that sometimes even the engineers who built the model can't tell you exactly how it arrived at one specific conclusion. And this chart just drives the point home. We're not talking about some niche applications here. We are talking about healthcare, where it could be influencing a diagnosis. We're talking finance, where it's deciding your credit score, and even the legal system. These are all areas with profound, absolutely life-altering consequences. So, the crucial point here is that this isn't just some technical puzzle for data scientists to geek out on. No, this is a societal issue. How can we trust a system we can't understand? Who is accountable when it makes a mistake? And how in the world do we make sure it's being fair? The black box makes these vital questions almost impossible to answer. So, if our most powerful AIs are black boxes, how do we even begin to open them up? Well, that brings us to our first amazing tool. It's a method with roots in a pretty surprising place: cooperative game theory. It's called SHaP, and believe me, it's a real game changer. SHaP stands for Shapley Additive Explanations. Yeah, it's a mouthful, I know, but the idea behind it is just brilliant. It's based on the work of a Nobel laureate named Lloyd Shapley, and game theory is all about fairly figuring out who deserves credit in a complex team. So the creators of SHaP had this idea: what if we treat an AI's decision like a game? Every piece of information it uses, like age, income, medical history, is a player. The AI's final prediction, that's the payout. SHaP's job is to be the referee and figure out exactly how much credit each player gets for that final result. Let's break this down, because the game analogy is perfect. Imagine the game is to predict the price of a house. The players in this game are all the features: the size of the house, the location, how many bedrooms, you get it. And the payout? Well, that's the specific contribution that each of those features made to the final price. We call that its shape value. And this is where that additive part of the name just clicks into place. A prediction isn't some big, mysterious number. It's actually just the sum of its parts. You start with a base value, kind of the average prediction, and then each feature's SHaP value either pushes that prediction up or pulls it down. So like you see here, a big house might add a whopping $70,000 to the price, while being in a great location could add another $20,000. It's like a transparent, simple audit trail for the AI's final decision. And because SHaP is grounded in solid mathematical theory, it offers some really powerful guarantees. Its explanations are fair, they're consistent, it can explain one single prediction, what we call a local view, but it can also explain the AI model's behavior as a whole, a global view. And, this is crucial, it understands how different features interact with each other. It's incredibly robust. Okay, now let's meet our second tool, LIME. It takes a completely different path to get to the same goal. If SHaP is our rigorous game theorist, think of LIME as the fast-moving, boots-on-the-ground local detective. LIME stands for Local Interpretable Model Agnostic Explanations, and its approach is really clever. Instead of trying to analyze the entire, super complex model, LIME just hones in on one single prediction at a time. For that one instance, it builds a simple, temporary surrogate model that just mimics what the big model does in that tiny neighborhood. And that model-agnostic part, that's its superpower. It means LIME doesn't care what kind of black box it's investigating. It can work on any of them. The process our detective uses is actually really intuitive. First, LIME focuses on one case. Then it starts asking a ton of what-if questions by just slightly tweaking the inputs around that case. What if the income was a little bit higher? What if the age was a little bit lower? By seeing how the model's prediction changes in response to those tiny nudges, it builds a simple, really easy-to-understand explanation for just that one decision. So the key takeaway for LIME is its sheer practicality. It is incredibly fast and efficient. This makes it perfect for applications where you need a quick, intuitive explanation on the fly. Think of a customer service bot explaining in real time why a transaction was flagged. Okay, so we've met the game theorist and the local detective. Both are trying to solve the same mystery, but they use totally different methods. So let's put them head to head and see what the trade-offs are. This table gives us a fantastic at-a-glance summary. You've got SHaP, built on that solid game theory, giving you both the big picture and the tiny details with high consistency. The catch? It can be slower because it's computationally intensive. Then you've got LIME, using those simple local models. It's blazing fast, but it only explains individual cases, and its consistency can be a bit variable. Sometimes a small change can lead to a surprisingly different explanation. So the crucial point is the trade-off. Do you need SHaP's theoretical rigor, or do you need LIME's real-time speed? All right, now that we understand the tools, let's zoom back out. Why is it so incredibly important to have these explanations in the real world? Let's talk finance for a second. If an AI model denies your loan application, regulations like the Equal Credit Opportunity Act in the US actually require the lender to tell you why. A simple computer says no is actually illegal. Tools like SHaP and LIME are what provide those specific compliant reasons, like the decision was based on your credit history and debt-to-income ratio. And this push for transparency is going global. The European Union's huge GDPR regulation gives citizens a right to explanation for automated decisions. This means transparency is shifting from being just a desirable feature to a fundamental, legally mandated requirement for any company using AI. And nowhere are the stakes higher than in healthcare. A doctor is not going to blindly trust an AI's recommendation for a complex treatment. But if an explainer tool can highlight the specific factors in a patient's lab results or their scans that led to the AI's conclusion, well, that empowers the doctor to validate that finding. It builds that crucial human-AI collaboration that we need to make life-saving decisions with confidence. So we have the tools, and we know why they're so important. But trust me, the work is far from over. So where is this exciting field headed next? Researchers are tackling some really big challenges. How do we make these methods even faster and more scalable for truly massive datasets? How do we integrate them into systems that need an explained decision in milliseconds, like in an autonomous car? And here's what's really exciting. Can we create hybrid models that give us the best of both worlds, maybe using LIME for a quick first look, and then running the more rigorous shape analysis in the background for a deeper dive? And that leaves us with one final, crucial question to think about. As artificial intelligence becomes more and more powerful, more integrated into our daily lives, we have to decide what we expect from it. Is the ability to understand these systems just another feature on a long list? Or is it something more? Is it a fundamental right in an automated world? The answer we choose won't just shape the future of technology, it's going to define the relationship between us and the intelligent systems we create.